A footprint, pressed into red mud, only a few centimeters across, 4 toes, splayed. The animal that made it was smaller than a house cat, and it has been dead for 249 million years. It is walking through a world that has just ended. The forests it passes are not really forests. They are recoveries, stands of pale, fast-growing horsetails on ground still gray with ash. The rivers run thick with sediment. The sea, when it reaches the sea, is almost empty. It does not know any of this. It knows that the ground is warm and that something small is moving in the leaf litter. It is hungry. It is fast. And it belongs, though no one will know this for another 248 million years, to a lineage that will one day include the largest animals ever to walk on land, the fastest, the most ornate, the most famous extinct creatures in human imagination. It belongs to the lineage of the dinosaurs. And right now, in this scorched riverbed in what will one day be southern Poland, it is no one. It is one small thing among 100 small things, none of them important. This is where the story starts. Not in glory, in a footprint, in a recovering world, in an animal that does not yet know it has been given anything at all. How does a world recover from nearly ending? And what crawls out of the ashes? This is Cosmic Canvas. This is the Mesozoic. This is Episode 1, Before the Throne. To begin, we have to imagine an emptiness. 252 million years ago, in the place we now call Siberia, the ground opened. Not in one place, in thousands. Lava welled up through cracks in the crust of the continent, and it kept welling up, on and off, for the better part of 1 million years. Before it was finished, it had covered an area roughly the size of the contiguous United States, in basalt several kilometers thick. The eruption was the largest of its kind in the last 500 million years of Earth's history. We call it the Siberian Traps. The lava itself was not the killer. The lava was only the messenger. What did the killing was what came up with the lava. Carbon dioxide by the trillion tons, sulfur dioxide, halogens, nickel-laden dust. The lava intruded into ancient coal beds and oil shales and set them on fire from beneath, releasing greenhouse gases on a scale the planet had not seen in hundreds of millions of years. The atmosphere warmed by 10 degrees Celsius. The oceans, in places, lost their oxygen. The forests died. And when the forests died, they stopped pulling carbon out of the air, so the air got hotter, and what was left of the forests died. Of every 10 species in the sea, 9 were gone. On land, 3 out of every 4 vertebrate species disappeared. Whole orders of life, animals that had flourished for 200 million years, simply ended. We call this event the End Permian Extinction. The scientists who study it call it, more honestly, the Great Dying. It is the worst thing that has ever happened to life on Earth. For 5 million years afterwards, the planet stayed broken. The greenhouse persisted. The tropics were too hot for most things to live in. Coral reefs took 10 million years to rebuild. The forests that returned were not the old forests. They were stranger and sparser, dominated by a few species of conifer and a handful of survivors from the older world. And it is here, in this slow recovery, that our story begins. because something walked out of the great dying. Several somethings, in fact. The mammal-like creatures called cynodonts survived. Small, fast-growing, already on the slow climb toward warm-bloodedness, scuttling under the feet of larger animals. So did the ancestors of turtles, of crocodilians, of the lizards. So did a group of small, lightly built reptiles called archosauromorphs, which would, in time, give rise to two extraordinary lineages, the crocodile-cousins and the bird-cousins. The bird-cousins are the ones we are following. In 2010, a team of paleontologists working in the Holy Cross Mountains of Poland found a set of footprints in red Olenekian age sandstone, dated to roughly 249 million years ago. The prints were small, four-toed, slightly digitigrade, meaning the animal walked on its toes rather than flat-footed. They belonged to no known dinosaur, but they belonged structurally, anatomically, unmistakably, to the lineage from which dinosaurs would come. They are called Prorotodactylus. They are footprints of the dinosaur stem line, and they are dated to within 3 million years of the Great Dying itself. Which means this: the lineage that would become the dinosaurs was already walking through the recovering world. While the planet was still grieving, the ancestors of Tyrannosaurus and Triceratops and Brachiosaurus were already taking their first quiet steps in a Polish floodplain. They were small. They were unimportant. They were waiting. This is the first thing we have to unlearn. For most of the 20th century, the textbooks said that dinosaurs appeared in the Late Triassic, around 230 million years ago, and rapidly conquered the planet because they were better than what came before. Faster, smarter, more efficient. The other animals, the textbooks said, could not compete. It is a very tidy story. It is also wrong. The new picture is messier and stranger, and considerably more interesting. The dinosaur lineage existed for tens of millions of years before any dinosaur mattered. They were a minor branch on a crowded tree. The world was full of other things, larger things, more spectacular things, more successful things. And the dinosaurs lived around the edges of those things for a very long time. They were not the heirs. They were the bystanders. To understand how they finally inherited the world, we have to meet the things that owned it first. The continent in this story has a name: Pangaea. There is only one. From pole to pole, one landmass, the size of all our continents put together, surrounded by a single world ocean. You could, in principle, walk from what will one day be Beijing to what will one day be Buenos Aires without ever crossing salt water. The interior of Pangaea is vast and hot and dry, a desert larger than any desert that exists today. The coasts are wet. The poles are temperate. There is no ice anywhere on Earth. And on this single continent, in the long quiet after the Great Dying, two great groups of animals are slowly rebuilding the world. The first group is the synapsids. These are our relatives, the lineage that includes the cynodonts and the dicynodonts, and eventually, the mammals. In the Permian, before the Great Dying, the synapsids ruled. They were the lions and the elephants of their age. The Great Dying nearly finished them. But it did not. Some of them survived, and in the early Triassic, the survivors began to grow. Imagine an animal the size of a pig, with a beaked face like a turtle, two short tusks curving down from the upper jaw, walking with its legs splayed slightly outward. This is Lystrosaurus. It is one of the most successful land animals that has ever existed. In the years after the Great Dying, Lystrosaurus fossils appear on every continent, in places that were once parts of Pangaea, separated by thousands of kilometers. For a few million years, almost every large vertebrate on Earth was either a Lystrosaurus or something trying to eat one. The synapsids are the survivors. They are the inheritors. And as the Triassic deepens, their descendants get larger. By the Late Triassic, the dicynodonts have produced an animal the size of an Asian elephant. We call it Lysowitzia boyani. It walked on pillar-like legs, weighed somewhere between 5 and 7 tons, and was found, like Prorotodactylus before it, in the Badlands of southern Poland. It was a plant-eater, a beaked browser, a giant of the warm latitudes. And it is here, not in a brontosaurus, not in a sauropod, not in any dinosaur at all, that the Triassic produces its first true giant. The dinosaurs at this point are still the size of dogs. The second group on Pangaea is the archosaurs. These are the reptile lineage, and within them, two great branches part company. On one side, the bird line, the ornithodyrans, small, lightly built, walking on the tips of their toes. The pterosaurs evolved from this branch and took to the air. The dinosaurs evolved from this branch and stayed on the ground. On the other side, the crocodile line, the Pseudosuchians, heavier, armored, built like tanks. And in the Triassic, this side was winning. The Pseudosuchians produced some of the most spectacular predators of the entire Mesozoic, and almost none of them are famous, because almost none of them survived. There was Postosuchus, a 4-meter carnivore from what is now Texas, capable of rearing up onto its hind legs like a small Tyrannosaurus, though it lived 100 million years before any Tyrannosaurus existed. There was Saurosuchus, a 7-meter apex predator from Argentina, weighing as much as half a ton, with teeth like steak knives. There was Smok, from Poland, of disputed identity, but probably another giant Pseudosuchian, leaving great chambered droppings full of crushed bone. And there were the phytosaurs, long-snouted, crocodile-shaped fish-eaters that lined the rivers in such numbers that, if you had visited a Triassic riverbank, you would not have believed there could be room for anything else. They were not crocodiles. They were not even close to crocodiles. But they had become crocodile-shaped because the riverbank was a crocodile-shaped place, and the same shape kept getting reinvented to fill it. These are the wrong winners. The lineages that, in any reasonable Triassic betting pool, you would have put your money on. They were larger than the dinosaurs. They were more numerous than the dinosaurs. They were more diverse than the dinosaurs. Every advantage was on their side. And then they were gone. But not yet. About 234 million years ago, the climate broke. Volcanic eruptions on the western edge of Pangaea, a flood basalt province called Rangelia, pumped enough carbon dioxide into the air to push global temperatures up sharply. The hydrologic cycle intensified. The interior of the supercontinent, which had been bone dry for millions of years, began to receive rain. A great deal of rain. The rain fell, on and off, for somewhere between 1 and 2 million years. The geologists who first noticed this anomaly in the rock record gave it a name: the Carnian pluvial episode. It was not a constant downpour. It was a series of wet pulses across a couple of million years, separated by drier intervals. The new evidence from lake beds in northern China, analyzed in detail in recent years, suggests 4 distinct pulses of warming and rainfall, each triggered by a separate phase of volcanic activity. But the effect on the world was profound. The drylands of the supercontinent bloomed. New plant communities replaced the old. The seed ferns that had dominated Triassic floras began to give way to early conifers, taller, tougher, easier to chew. And the animals that could eat the new plants did well. The animals that could not, did not. Among those that did well were the dinosaurs. In the rocks of the Ishigualasto Formation, in what is now northwestern Argentina, dated to about 231 million years ago, just after the Carnian pluvial episode, we begin to find them. Real dinosaurs. Not the ancestors of dinosaurs, not the cousins of dinosaurs, but dinosaurs themselves. They are not what you expect. Eoraptor, the dawn plunderer, is about the size of a fox. A meter long, perhaps 10 kilograms in weight, walking on 2 slender hind legs with 5 small fingers on each hand, and a mouth that holds both leaf-shredding teeth and meat-tearing teeth. It eats whatever it can catch and whatever it can pick. It is one of the earliest dinosaurs we have ever found, and it is unremarkable. Herrerasaurus is larger, 3 to 6 meters long, perhaps 200 kilograms, a slender bipedal predator with clawed, grasping hands and recurved teeth. It is one of the earliest predatory dinosaurs we know. And in the Ishigualasto fauna, it is not the apex predator. The apex predator is a pseudosuchian. Herrerasaurus is a mid-level hunter, scavenging from larger kills, taking smaller prey. It walks among the rhynchosaurs and the dicynodonts and the great crocodile-cousins, and it is one animal among many. Eodrameus, the dawn runner, is smaller still, about 1 meter long, perhaps 5 kilograms, fast, light, and built for speed. This is the dinosaur Dawn. Not a thunder of feet across the plains, a handful of dog-sized animals in the margins of an ecosystem ruled by other things. For a long time, paleontologists assumed this stage was brief, that within a few million years of their appearance, dinosaurs outcompeted the older fauna and took over. The data did not really support this, but the alternatives were vague, and the story was tidy, and so the story persisted. In November of 2024, a team led by Martin Kvarnström at Uppsala University in Sweden, working with the Polish paleontologist Grzegorz Niedzwiecki, published a study in the journal Nature that took a different approach. They did not look at bones. They looked at what dinosaurs and their contemporaries had left behind, biologically speaking, on the way through. They looked at over 500 fossil droppings, fossil vomit, and fossil gut contents, collectively bromelites, from the Polish basin, spanning the late Triassic to the earliest Jurassic, a window of about 30 million years. The contents were astonishing. Bones, sometimes in pieces, sometimes whole, from the droppings of an animal called smok, a giant Polish pseudosuchian that crushed bone like a modern hyena. Fish scales, plant fragments, bivalves. And in one of the most exquisite finds in the entire study, inside a coprolite belonging to Silosaurus, a small beaked dinosaur cousin, an entire fossilized beetle, antennae and legs intact, of a species new to science. From these contents, the team reconstructed who was eating whom, and how that changed over time. What they found was that the rise of the dinosaurs was not a takeover. It was a staircase. 5 distinct steps, each one a different ecological configuration, each one separated from the next by tens of thousands or hundreds of thousands of years of environmental change. First, dinosaur precursors, small, omnivorous, eating insects and roots and whatever they could find. Then, after the Carnian pluvial episode, the first true predatory dinosaurs, fish-eating and insect-eating theropods. Then, after another climate shift, the first herbivorous dinosaurs, with droppings full of fern fragments. Then larger herbivores, eating tougher plants. And finally, in the latest Triassic, the first truly large theropods, animals that had begun to look like the dinosaurs of legend. Each step was a response to something, a change in climate, a change in plant communities, the extinction of a competitor. The dinosaurs were not winning by being better, they were winning by being adaptable. Small enough, generalist enough, fast reproducing enough to take advantage of doors that kept opening for reasons that had nothing to do with them. It took 30 million years. For 30 million years, dinosaurs were not the main characters of any ecosystem they lived in. They were the supporting cast. They waited. And then something else happened. 201,564,000 years ago, a date we know to the nearest few tens of thousand, the ground opened again. Not in Siberia this time. In the center of Pangaea, along a line that today runs from Morocco to Newfoundland to Brazil. The supercontinent was beginning to tear itself in two. Where it tore, lava came up. Over the next 600,000 years, several million cubic kilometers of basalt would pour out of the cracks in the crust and cover an area roughly the size of Australia. The geologists call it the Central Atlantic Magmatic Province, CAMP for short. It is the largest known continental flood basalt province on Earth. And it killed about 3/4 of all species alive at the time. For a long time, the assumption was that the killing mechanism was familiar, the same as the Great Dying, only smaller. Volcanic carbon dioxide pumped into the air over thousands of years, warming the climate, acidifying the oceans, suffocating life by slow degrees. There is good evidence that this happened. The end Triassic does show the chemical fingerprints of a warming world, an acidifying ocean, an atmosphere out of balance. But in October of 2024, a team led by Dennis Kent at Columbia University, working with Paul Olson and colleagues, published a paper in PNAS that complicated the story. They had been studying the timing of the camp eruptions in extraordinary detail, using paleomagnetism to align lava flows across what are now Morocco, the eastern United States, and the Bay of Fundy in Canada. What they found was that the eruptions did not occur as a slow, steady release. They occurred in pulses. Each pulse was geologically brief, perhaps less than a century, and each one released vast quantities not only of carbon dioxide, but of sulfate aerosols. Sulfate aerosols do not warm the atmosphere. They cool it. They reflect sunlight back into space. The team's conclusion was unsettling. The killing blow at the end of the Triassic may not have been heat. It may have been cold. Each pulse of camp volcanism may have produced what we would now call a volcanic winter. Global temperatures crashing for a few years or a few decades, photosynthesis collapsing, food chains failing. They compared it to a much smaller event we have witnessed in human history, the 1783 eruption of the Laki volcano in Iceland, which caused one of the coldest years on record and led to widespread crop failures across the northern hemisphere. Camp was hundreds of times more powerful than Laki, and it pulsed again and again for tens of thousands of years. Imagine a world that had been warm for 200 million years. Imagine the sky going gray. Imagine the temperature falling week after week until the leaves did not unfurl in spring. Imagine this happening not once, but a dozen times, with decades of recovery in between. Imagine being a large, slow, warm-loving reptile in such a world. It is a story we are still piecing together. The exact balance of cooling and warming is still argued. The relative contribution of CO2 and sulfate is not settled. But what is clear is this. The end Triassic extinction was a complicated, multi-pulse event, and it preferentially killed the large. The phytosaurs vanished. The etosaurs vanished. The Rauisuchians vanished. The great pseudosuchian predators of the Triassic, the Postosuchus and the Saurosuchus and all their relatives, were gone. Lysowicia was gone. The giant dicynodonts were gone. The crocodile line, which had dominated the Triassic, was reduced to a few small, mostly aquatic survivors, animals that would, in time, give us the modern crocodiles. The synapsid line, which had dominated before that, was reduced to small, furry, nocturnal cynodonts, animals that would, in time, give us the mammals. And us. And the dinosaurs? The dinosaurs walked through. We do not entirely know why. They were not all small. By the end of the Triassic, some sauropodomorphs were already approaching the size of a small elephant. They were not all simple. They were a varied group. But for whatever combination of reasons, perhaps their slightly elevated metabolisms, perhaps their efficient lungs, perhaps the way they nested and grew their young, perhaps simply luck. When the volcanic winters came, more dinosaur lineages survived than pseudosuchian lineages did. And on the morning after the extinction was over, which is to say, in the geological dawn of the Jurassic, about 201 million years ago, they walked out into a world that had finally been emptied of competition. Now think about what just happened. For 30 million years, the dinosaurs were not important. They appeared in the late Triassic. They survived the Carnian pluvial episode. They slowly diversified into the niches that climate change opened for them. But they were always one group among many. Smaller than the dicynodonts, less spectacular than the Rauisuchians, less abundant than the phytosaurs. And then, in the span of a few tens of thousands of years, every one of those rivals was gone. Not because the dinosaurs killed them, not because the dinosaurs outcompeted them, because the Earth itself, for the second time in 50 million years, broke. This is what we used to think, that the dinosaurs took over because they were better. This is what we now know, that the dinosaurs took over because they were there. They were small enough to wait through what larger animals could not. They were varied enough that at least some of them survived what killed the rest. And when the smoke cleared, and the cold lifted, and the sun came back, theirs were the footprints in the ash. The throne was never won. The throne was inherited. In a Polish floodplain in the late 20th century, a paleontologist named Grzegorz Niedźwiecki spent years walking back and forth across a clay pit looking for fossils. He found, eventually, the bones of Lisowicza, the elephant-sized dicynodont that should have been the king of the late Triassic and was not. He found, eventually, the droppings of dinosaur ancestors going back through 5 distinct ecological steps, told in the contents of vomit and feces and gut linings preserved in stone. And he found, eventually, the small 4-toed footprints that took the lineage of the dinosaurs back to a moment within 3 million years of the worst extinction in the history of life. The footprints were not made by anything famous. They were not made by anything large. They were made by a small, fast, warm-running animal walking through a world that had just ended. An animal that had no idea what it was, and no idea what it would become, and no idea that 249 million years later, a thinking species would lean over its tracks and try to understand them. There is something almost humbling about this. The lineage that produced the largest, the fiercest, the most ornate land animals in the history of the world began as a series of unremarkable footprints in a recovering swamp. The animals that we now imagine as titans were, in their first millions of years, simply small things, waiting for larger things to fall. We are still looking, of course. We do not have all the footprints. We do not have all the bromelites. We do not have all the answers. The argument about why dinosaurs survived the end of the Triassic when so many other lineages did not is an argument that scientists will be having for decades to come. But what is no longer in doubt is this: the rise of the dinosaurs was not a triumph. It was a survival. And what survived was something none of the great Triassic predators ever had: a willingness, built into the architecture of their small, hot-running bodies, to be patient. In the next episode of this series, we will follow what happened next. Because once the throne was inherited, the dinosaurs did not simply sit on it. Within 20 million years of the end of the Triassic, something extraordinary will happen to the metabolism of one of their lineages. Something that will allow them, for the first time, to walk through the cold without slowing down. Something that will eventually give them feathers, and songs, and flight. The thing the world's first dinosaurs had, that flicker of inner warmth that helped them survive a volcanic winter, was about to turn into a furnace. And from that furnace, in another 135 million years, would come every robin that has ever sung in a garden at dawn. This was the world before the throne. It is not where the story of the dinosaurs begins. It is where it survives long enough to begin. This is Cosmic Canvas. Until next time.